So if you've already gone through the lesson, some of this stuff might be information that you already know about. Otherwise, this will help you quickly go through this lesson if you haven't yet. So weighted isotopes. We're going to identify, excuse me, the structural differences between isotopes of elements, and we're going to determine the weighted average mass of an element when given the appropriate data. So we're going to start off here with a little warm-up question, which is something that we should all know. What are the parts of an atom? We're talking about major parts here, not like super, deep physics parts. And not only that, but how can we use the periodic table to help us identify those parts? So take a moment right now, look at a periodic table if you need to, think about what parts of the atom you do know, and type in the chat any information you can give me for this warm-up question. In fact, I'm going to get a periodic table open while you guys are thinking about this one. Periodic table. Okay. Okay. So still waiting in the chat for some ideas on, not that, where'd my PowerPoint go? Too many tabs open. There we go. On what are the parts of an atom and or how we can tell from the periodic table any of that information. Okay, awesome. Bella is starting us off here with a solid answer. Protons, electrons, neutrons. Perfect. The periodic table shows us how many protons, neutrons, and electrons are in one atom of an element. Perfect. Right? So in case we're not sure how that works, we're going to review that just really quickly here. So let's say that we look at the element rubidium. Oh, I didn't even know this thing would like pull up all this detailed information. It links you right to the Wikipedia. Very cool. We don't need all that information. But let's say we're looking at rubidium, which on the periodic table is element number 37. How, Bella, or maybe someone else, would we know how many electrons or how many protons are in an atom of rubidium? Any ideas on how we would be able to tell how many protons or electrons are in an element, or excuse me, in an atom of rubidium? Thank you, Bella. Glad you're with me today. The atomic number or the atomic number / atomic mass are going to be what we need to look at here. So rubidium has an atomic number of 37. So what that means is that in a neutral atom of rubidium, we will have 37 protons, right? That we get just straight up from the atomic number. That never changes. And we would have 37 electrons, right? This isn't a neutral atom because keep in mind, we're not always dealing with neutral atoms in this class. However, if the atom is neutral, meaning it doesn't have a charge, we have to have the same number of protons as we have electrons. So if we have 37 protons, we have to have 37 electrons. Otherwise, the atom would have a charge. Charged atoms are another thing. We're not going to really talk about them right now, right? But that is important to note that sometimes those electron numbers might be different. Now, why couldn't we change the number of protons, though? What happens if we change the number of protons in an atom? Does anyone have any ideas? Like, what happens if we took a proton away from rubidium, or we added a proton to rubidium? Would it still be rubidium? Yeah, it would change the charge for sure, right? But it would also change the element. Because remember, these atomic numbers tell us not only which element it is, but how many protons they have. So if something has 36 protons, it's no longer rubidium, it is now krypton, right? If something had 38 protons, it would be strontium, not rubidium. So the protons can't change unless we want to change the element, right? Which is a whole different thing. We also want to know about neutrons. So Bella, since you're the only person talking to me, everyone else start talking too. How do we figure that out? How do we figure out neutrons? Okay, Michelle, you had an excuse, but no more. How do we find neutrons? Just from looking at the periodic table, we're still talking about rubidium here, Rb, number 37. How would we figure out how many neutrons are in a neutral regular atom of rubidium?
So taking this and moving into the human form, where are you wanting to start? Do you want to start with what you're kind of work, or do you want to work with the body?
This one's the hardest. Is it the same as the number of protons? That is a good guess from Bella, right? Then maybe 37, 37, 37. Not exactly, right? Neutrons are actually going to be equal to our atomic mass minus our number of protons. So I'm going to go back to my PowerPoint after I write down what our atomic mass is so that you can see what I'm typing a little bit easier. It is 85.468. Okay, so I get that atomic mass straight off the periodic table. In this case, it's on the bottom of the periodic table. On other periodic tables, it might be on the top, right? You just kind of have to look at the key to see what you're dealing with. But in this case, we have to do some subtraction, which is why neutrons are the hardest. So we know that neutrons are going to be our atomic mass minus the number of protons, because in an atom, our protons and our neutrons have pretty similar mass. They are the main portion of what makes up the mass of an atom. Electrons are very tiny, right? They have very small mass. Usually we neglect the mass of an electron, and we only focus on protons and neutrons. So when we're doing this work, we actually round our atomic mass number. In this case, it's 85.4, right? So we're going to round this to 85 because we don't want to have part of a neutron, right? We'll also talk about why that number is a decimal like that in this lesson, actually. So we're going to say 85 is our total atomic mass minus how many protons? Well, we already figured out 37 protons just from looking at the atomic number. And what do we end up getting if we subtract 37 from 85? We get 48, right? Which tells us that we have 48 neutrons in an atom of rubidium. So the same thing would apply for any element, right? If you know the atomic mass and you know the atomic number, which you should because you'll have access to a periodic table, you can figure out protons, neutrons, and electrons for any element. Very helpful information there, because sometimes people forget that that is actually found on the periodic table. So, isotopes, right? Real life connections. Why do we use them? Why do we care about them? What is the purpose? So we're going to talk about the real life examples first, and then we're going to talk about what an isotope actually is, right? But in this case, one of the biggest pieces of evidence that a meteor actually was what wiped out the dinosaurs comes from an isotope, right? Iridium and osmium, which are two elements found in layers of the earth at the correct time, right? So the correct age and geologic time, these two elements are not really found on Earth, right? They exist in very, very tiny, tiny quantities. However, in space, they're very common. So in meteors and asteroids, you see tons of iridium and osmium. So in this layer of rock, the scientists discovered this black line here, right? It looks very differently colored than the rock around it. That's actually a layer of iridium and osmium. Just a nice fine layer in geologic time found at the correct boundary here, right? This is one of the biggest pieces of evidence that a meteor was involved in wiping out the dinosaurs, because how did these things get in a layer on Earth if a meteor was not the cause? Right, there could be other explanations. Perhaps Earth was different at that time, right? Maybe there was a higher concentration of iridium or osmium or whatever. However, for the most part, scientists agree that this does support the idea that, oh, hey, wait a second, these elements are existing here. They must have come from a meteor. Another example is in medicine, right? You hopefully haven't had to do this, but maybe you have. Maybe someone in your family that you know has. But you can actually drink a radioactive element that's not harmful. I put that in quotations, right? Because technically all radiation is harmful to you. But you can actually drink something radioactive for doctors, to be able to see something that's going on inside your body, right? So for example, maybe you have something wrong in your stomach, right? Or in your intestines or in your heart, which are kind of hard to get in with a camera, right? How are you going to get in to see what someone's heart's doing on the inside without cutting it open? Well, in this case, you can have them drink something radioactive, and then you can actually put them under imaging that will show where that radioactive element is. So in this case, it'll show that it's in someone's stomach, right? And it will glow, as radioactive things tend to do, right? So a little bit scary, but a very realistic and useful way that doctors use radioactive isotopes to actually try to help figure out different diseases or different issues that people are having. Final real life connection kind of relates to the first one, but it's really about radioactive dating, right? If you've taken earth science already, or you may remember from middle school, you've probably talked about this already. We use carbon-14 a lot, right? There are other ones we can use, but we can use isotopes of certain elements to figure out how old something is based on how quickly they decay. So, for example, when something is fresh, brand new, there will be 100% carbon-14 present, right? And after, let's see, after 10, is that a 10? 8.5, maybe 9 years, we will see only about 50%, looks like it's around 10, of that carbon-14 left, right? And then once we get all the way to 44 years, then we barely see any. We would see like 2%. So we can actually use these isotopes to figure out how old something is. This is pretty common in finding out, like, if bones are discovered, right, like a grave site, and potentially maybe they think, oh, this could have been a murder, right? This could be used to find the right age of something. Naming isotopes. So there are two ways that we may see these isotopes named. They will always have a number associated with them, which we will talk about in a second. And you may see the number written as a superscript. You may see it written as a dash. So what does that actually mean, right? Well, that's telling us the atomic mass. So carbon normally has what atomic mass? Let's check it out on the periodic table. Carbon's atomic mass is usually 12, right? 12.011. Okay, so if we have something called carbon-14, what does that mean? What does that mean to have carbon-14? If we have a bigger atomic mass, it's positively charged. That's a good guess. No, isotopes are still neutral. They're still a neutral substance. in this case, right, we're going to talk about carbon. So carbon usually is 12.011 as its mass. In this case, we're saying carbon 14. So we talked about before, you can't change the protons, right? Because if we add protons to carbon or take protons away, then we don't have carbon anymore. We can't change the electrons because we have the same amount right now in carbon. So the only thing we can change is the neutrons, right? Because neutrons don't have a charge, they're not going to impact the charge. The only thing they will impact is the mass. So think of it this way, a regular carbon atom has 6 electrons, 6 protons, and oddly enough, 6 neutrons, right? Which again, I can figure out by saying its atomic mass is 12, its atomic number is 6, right? Which is where I got the 6 for the protons and the electrons. Well, 12 minus 6 is 6, so there are also 6 neutrons. Well, if we're talking about carbon 14, which now weighs 2 units more, how many neutrons would we have in a carbon 14 molecule? We would have 8. So in carbon 14, we're going to still have 6. I'm going to do protons first, actually, because that is more logical. 6 protons, 6 electrons, right? It's still neutral. But now we have 8 neutrons. What about if we had carbon 22? I don't even think that exists, but let's pretend it does for a second. How many electrons would we have? It's kind of a trick question. We would still have 6 protons, 6 electrons, because it's still carbon, but how many neutrons would we have now if we have carbon 22? 16. Now, let's say I don't know how to figure that out. Well, all you have to keep in your mind is that protons plus neutrons equals atomic mass. So if that's true, which I'm telling you it's true, why can't I select that? Let me see. Sorry, trying to move. Oh, that's in the same box. Okay, I didn't mean to put that in the same box, but that's okay. Protons plus neutrons are going to equal the atomic mass. So if I'm being told the atomic mass is 14, and I know that I have 6 protons, right, I'm just going to do 14 minus 6 to get my number of neutrons. Same thing here for carbon 22. I know my atomic mass is now 22. I still have 6 protons, so I'm going to do 22 minus 6, right, and get 16. So if you can keep in your mind that protons and electrons are not changing here, right? We don't usually see charged isotopes. It's not really a thing necessarily. Really, only thing you have to worry about is the neutrons. So, what is changing in an isotope? I kind of got ahead of myself. I went through this already, which I tend to do. But the only thing changing in an isotope is the neutrons. Because protons can't change, right? Electrons can change, but in this case, they're not going to because we're not changing the charge. Neutrons are the only thing left that we can adjust that will impact atomic mass. So, now we're going to practice. I just told you about how to do this with carbon. Well, now we're going to talk about with hydrogen, a different kind of carbon, and a uranium. So, if you feel like you already know how to do this, go ahead and start doing it on your own. If you're not sure, I'm going to write out some steps for you. 1, find the regular, atomic mass, right? You can do it that way. Actually, no, let's not even do it that way. I'm going to make it even simpler. Find the atomic number, protons plus neutrons equals atomic mass. So subtract using new atomic, or I guess using isotope atomic mass. So I'm going to give you guys about 30 seconds here, maybe a little longer, 45 seconds. I want you to go look at a periodic table, see if for each one of these, so each element listed here, see if you can find the protons, the number of protons, the number of electrons, and the number of neutrons for each element listed here. And we will go over it in just a moment. All right, and Michelle, I know you're driving, so kind of hard for you to interact with the periodic table in your car, but I hope you're listening and absorbing. So first element we're gonna look for is hydrogen. And what are we looking for? We're looking for its atomic number. You may have memorized this, right? Because hydrogen is a pretty frequently used one, it's very common. We see that hydrogen has a atomic number of 1, which tells us, which tells us what? Tells us our protons. So we know hydrogen has 1 proton. Well, how many electrons is it going to have? 1, right? Why? Because protons and electrons have to be equal in a neutral atom. I don't see any charges over here, right? So it's neutral. What about neutrons, though? How are we going to figure out how many neutrons are in hydrogen 3? Well, we're going to take our atomic mass and we're going to subtract our protons, which in this case is going to be 3 minus 1 equals 2. So we have 2 neutrons in hydrogen 3. Regular hydrogen just has 1. So this is heavier, right, than a regular hydrogen atom. Okay, what about carbon 13? Carbon I kind of talk about quite a bit here, but for carbon, we already know from before we have 6 protons, we have 6 electrons. So how many neutrons are we going to have in a carbon 13 molecule? How many neutrons will we have? Glad to see you're back, Vitali. We are figuring out how many neutrons would be in carbon 13 isotope. Well, if we aren't sure, right, we can set up an equation. We know protons plus neutrons equals atomic mass. So if we plug in what we know we have 6 protons. We don't know how many neutrons we have. And we know that that has to equal an atomic mass of 13. 1 more than 6 is a correct answer, yes, Bella. So we're really going to be doing 13 minus 6 here, which means we will actually end up getting that we have 7 neutrons. Right? And that is a valid way to think about this. If you know what the regular atom has, you can always see how many more or less it must have based on this. However, a lot of times you're going to get elements that you might not remember how many protons are in it, right, or how many neutrons are in it. Okay, so let's try uranium 235. First step, go look at uranium on the periodic table, and you guys tell me what is the atomic number or the number of protons in uranium. How many protons, or what is the atomic number of uranium? Okay, nobody's talking to me, guys. Like, I already know how to do this. So if you're not going to participate and at least guess or say I don't know or say I'm not sure how to do it, right, then I don't know where to go from here because I already know how to find all of these things. So how many protons are in a regular uranium or any kind of uranium, because protons can't change? How many protons are in uranium? You're looking for the element on the table. Okay, yeah. So if you can't find it, that's different. Let's see. I don't even remember exactly where it is. Let's see. Uranium is number 2. Yeah, where is uranium? Somewhere around here. It's like 200 and something is the mass. So it's got to be somewhere around here. Read on francium. Da-da-da. Yeah, that is weird. Well, no wonder. That's why you guys aren't talking to me, because you can't find uranium on the table, and I'm not seeing it either. So, you know what we'll do? We'll Google, which is always the answer for when you can't find something on the periodic table. It is number 92. Okay, so now we'll come back to the table and see where that is. Okay, so it is actually down here. There it is. It's in the weird little part of the periodic table that gets taken out. So that might have been why you couldn't locate it, right? So, okay, we've located it now. So how many protons are in uranium? $92. How do we know that, right? It's the atomic number of the element, right? So then how many electrons must there be? 92, because it's a neutral atom. There's no charge. Positive and negatives have to cancel. How many neutrons would be in uranium-235? Okay, I'm seeing guesses. 95, Bella guesses. Why did you guess 95, Bella? I'm not sure where you got that, but I will try to help you here. Vitaly is correct. It is 143. How do we know that? Well, we took our atomic mass from our isotope 235 and we subtracted our protons. 92, which equals 143. 95, I'm guessing maybe you were looking at the mass. Oh, okay, you did it back. Okay, yeah. So really, it's just about taking your number they give you for the isotope and subtracting the protons out. So in this case, 143 is correct. Okay, hopefully you guys are feeling pretty good about that. Remember, if you can't find something on the periodic table, there is no shame in Googling. I mean, there's a ton of things on there. You might even have just skimmed right past it and not seen it, right? Because I know that happens to me all the time. So again, just to reiterate, well, then what are we seeing on the periodic table when we see this mass number that is not a whole number, right? We just talked about how protons and neutrons basically have a mass of 1 each, right? And they add up to be a mass. Well, if that's true, how come oxygen has a mass of 15.999 on the periodic table? Well, the mass on the periodic table is actually the weighted average of all isotopes known of that element. Now, what does a weighted average mean? It means that we put more emphasis on the number that's more common. So, for example, right, think about in your classes, tests usually are weighted more than assignments, right? Because they're given more points or more percentage of your grade because they're more important sometimes. In this case, though, we're talking about elements, right? Well, we want to know which element is the most commonly occurring. So let's talk about oxygen here. We have 3 isotopes of oxygen. Most elements have 2 to 3 isotopes. Some have more, some have less, right? We're still finding some of these things out even. So there may be more elements of or isotopes of oxygen that we just haven't even found yet. We also know our masses of these isotopes, right? Oxygen 16 is what we would call regular oxygen, right? It has 8 protons. We know that from its atomic number. It also would have 8 neutrons. Oxygen 16, or the most common one, right, is 99.762% of the world has that oxygen. Oxygen 17 and 18 exist, however, very small percentages, right? Not even 1% of oxygen on Earth is having these isotopes. So what we do is we set up an equation to figure out this mass here on the periodic table, or what the weighted average would be, and we do that by multiplying by the percent times the mass and adding them up, which we're going to go through in a little bit more detail, but there's an example of how they did that right here. Biggest, trickiest thing about this is sometimes people just want to straight up multiply by the actual percent number, and we do have to move the decimal, right? We're multiplying by a percent. We're finding the percent of that mass. So you have to multiply by a decimal here, not a whole number, or not the number they give you at the very least. So what does that look like? Well, here's an example that we're going to do. Copper has 2 naturally occurring isotopes. Copper 63 with an atomic mass of 62.94 makes up 69.17% of the sample, and copper 65 with an atomic mass of 64.93 makes up the other 30.83%. Calculate the weighted average atomic mass of copper based on the given information. Please give your answer in a total of 4 significant figures. So first thing that we do is we figure out, okay, what kind of copper do we have? Well, we have copper 63. Its mass is 63, right? But in this case, it is 62.94. Cool. Well, now we need to multiply that by the percent that makes up, that is made up of that copper sample. So in this case, we're going to multiply by 0.6917. All I did was take my percent and move my decimal 2 places to the left. That's what you're going to do every single time. Right? That's a shortcut, by the way. If you're ever trying to find like 69% of something, you just multiply by 0.69 and it will tell you. Right? So in this case, we have to move our decimal over 2 places so that we're actually finding the percent of 62.94. Then we have to add the other type of copper here, which in this case is copper 65, whose mass is 64.93. This time we're going to multiply by what?
It's terrible. I actually tried to sit down the other day, but
What will we multiply by here? For the first one, we multiplied by 0.6917. So what are we going to multiply our second copper mass by? Good, Vitaly. 0.3083. Right? Where did you get that number from? Well, that's the percentage of that copper. So if we do this math, right, which again, you're going to have to do your multiplication first, right? PIMDAS, as it is known, we do 62.94 times 0.6917. We get 43.53, we'll round it to 54, plus 64.93 times 0.3083, and we get 20.02. And if we add those two things together, plus 43.54, we end up getting a total of 63.56 AMUs. Now, does that make sense? Well, let's think about it. Most of the copper sample, 69% of it, was made up of copper 63, whereas 30% was copper 65. So it makes sense that we get an answer that's more close to 63, right? Because 69% of the sample is copper 63. So that's kind of what a weighted average does, is it's going to count the 63 more than it counts the 65. Okay, so now you guys are going to try one. It seems really simple, and it is. It's basically like a formula, but part of it is kind of understanding why you're doing that. So 3 isotopes of argon, which is Ar, occur in nature. Argon 36 makes up 0.337%. Argon 38 makes up 0.063%, and argon 40 makes up 99.6%. Calculate the weighted average atomic mass, giving your answer in a total of 5 significant figures this time. So type a 1 in the chat if you want to try to do this one by yourself. Type a 2 in the chat if you'd like for me to set it up again. So first thing we're going to do is we're just going to start with one of our argons. These U's, right, are our unit here for our mass. So I'm going to start with this first one they gave me. Argon 36 has a mass of 35.968. Good, Bella. Well, am I multiplying it by 0.337 or 0.00337, right? So even when you get tiny, tiny decimals like this, that is still a percent. You still have to move your decimal place 2 places to the left when you set up your multiplication. So that can be really tricky. That's honestly the biggest mistake I see, is that people forget to move the tiny percents over, right? Because it's still a percent. We're going to be adding to that our second argon, which is argon 38, whose mass is 37.963. We're going to multiply that by what? Point 0.00063. Right? Because we already have 1 0 there, we have to move our decimal 2 places to the left. You should have 3 zeros in front of your 63 there. Again, those are going to give you some tiny results, right? I mean, that's not going to be very much. We know that, but it's what they're telling us. Meanwhile, argon 40, right, our final version here, is 39.962. Times what? What are we going to multiply for our percent for our last isotope here? Good, Vitaly. 0.996. Right, again, we just took our percent, we moved our decimal 2 places to the left, right? Or we divided by 100 is another way of thinking about that. Okay, so then if you guys do this math, you tell me what you get as the weighted average of this argon sample. Yeah, grab your phone. I want you to practice doing the calculations, right? I'm also going to do it. And I want to make sure that we can all get the same answer here, because that is part of it too, is making sure you're typing it in the calculator correctly. All right, I'm seeing if I get the same answer as you, Vitali. I'm just adding all my numbers up here. Oh, you messed up, okay. You're pretty close though. It's very close to the answer. And Bella, let me know what you get when you get an answer. Okay, I got the same thing as you, Talia. I got 39.947. And Bella, I'm hoping that's what you get as well, but that is also what I got. So again, the concept here is you take the atomic mass that they give you, you multiply it by the percent as a decimal. That is the trickiest part, especially when there's already zeros, because in your mind you think, oh, that's already been converted, but it hasn't. Right? You still have to move your decimal place 2 times to the left for every single percent. Okay, good. You got the same. Amazing. Okay, so that's the end. Now you're going to do an exit slip for the same kind of concept here, right? You're going to work with this imaginary element symbol X with 2 isotopes. In this case, I'm not telling you the percent of the second isotope. You can use some subtraction to figure that out. And you're going to give your answer in a total of 5 significant figures. This is a great opportunity. Write your workout. Show me everything you do, right? Because if you're getting stuck on something, this is the perfect opportunity to say, I think I did this right. Is this what you do? Right? I'm going to be looking at your math and giving you feedback on your math. So this is available in Canvas now. Because you two were actually in the virtual session, you will get full credit, right? Which I don't even need to give you a code word because I'm going to remember because there were only 2 people here. So you will get full credit for turning this in if you get the correct, answer. Again, though, if you don't, then we're going to work together on fixing your math. There's also a quiz in Canvas associated with this concept where they ask you to do this as well. Okay, does anyone of you two have a question about this or want me to explain something again, or you're feeling like, okay, I think I'm getting it, maybe you're ready to move on and try by yourself, which I hope you are. Which, by the way, that was like a really wordy, long question. So really, the thing is, type a 1 in the chat if you're like, okay, I think I can do this, right? I have a pretty good idea, at least I think I might be able to try it. Okay, good. Both of you are feeling that way. And if not, right, then write out what you do know or what you can do, and I will be correcting and helping you with that to get it solved. Honestly, in terms of math, this is some of the easier math in the class. So embrace it, right? understand what an isotope is. It's just a different number of neutrons. Most of them are radioactive. Otherwise, that's it for today. So I will see you guys next week.